This is Chris.
And this is my colleague, Kat. We are both freelance data scientists. Kat is based in Berlin, and I'm based in Hamburg.
Whew. It's been an eventful couple of years, hasn't it? It seems like nearly every week news is coming out about some new, super capable large language model, some super impressive image generator, or a fantastic image video understanding system. There's been lots of speculation about these big corporations that release these models nowadays. What kind of resources do they actually put in? For example, I've read that for building GPT-4, OpenAI actually invested something like tens of millions, up to $80 million is a figure I've read. Sounds completely incredible. But they must be using thousands, perhaps tens of thousands of GPUs, and training on these massive private data sets that we don't really know much about. It's easy to start feeling a little bit left behind. Is it really so that scaling is all you need? Do you just need to put on resources upon resources to get ever more capable models? And if that's the case, where does that leave us? The small teams, the open source developers, the PhD students, the GPU poor. We are not going to be the ones who set sail into the unknown with our armada of GPUs in search, perhaps, of a new frontier of foundation models. No, this is us in the tiny boat, a small team, a handful of GPUs, perhaps not even that, using mostly open data or small data sets that we've collected for ourselves. But we don't need resources to be clever. We just need to know about a couple of methods that can help us take an existing large model that somebody else has trained and make it work for us. But we gotta make sure that we don't row in the wrong direction, because over there'll be monsters. Models that we have put in our scarce resources with nothing much to show for. And that is why today we want to talk to you about 3 proven micro-budget methods for adapting an existing model to your needs. The first one will be transfer learning, an oldie but goldie, where you want to take an existing model trained on some task and make it work for a different task. The other 2, distillation and quantization, are all about taking a large model and turning it into something smaller, more manageable. All of these methods are micro-budget friendly, meaning they're suitable for small teams, at most a few GPUs with small data sets.
And to make it all more hands-on than a simple talk, we have prepared for you a companion repo on GitHub. And this repo contains, for each of the methods that we are going to talk about, one example workflow, one example notebook that's easily going to run on a laptop like this. So we invite you to clone this repository, run this later after the talk, and see for yourself how well the methods are working. So method number 1, micro-budget method number 1, transfer learning. This is going to be very familiar for many of you, I guess, but still, this is such an elegant and essential method that we want to start the talk off with this. In our example repo, we find the following computer vision task. We have this interesting botanical data set of flower images, 8,000 images of the flowers. They belong to 102 different species, and our task is to build an automatic classifier that can classify each of the image into the respective species. So it's 400 megabytes of image data. That's not massive, but if you think about it, if you want to train and develop a model from scratch, that may be a strain on our microbudget. First of all, you have to decide on the right architecture, maybe you have to experiment with the architecture, and also you have to invest a little bit of compute time to train this model from scratch. So can we do more with less? Can't we take one of those well-working and proven image classifiers that are out there, for example, the MobileNet V2. It's an elaborate architecture, a deep convolutional neural network of 53 layers, about 3.5 million parameters, and it has been shown to have good accuracy on the famous ImageNet dataset. ImageNet is well known as a benchmark, 1.4 million images belonging to 1,000 different classes of objects, and this is truly massive. It's 150 gigabytes of images. So here's a proven image classifier, but it's for the wrong task. And here comes the basic idea of transfer learning. We have this model pre-trained for task A, usually on a very large data set that is beyond our microbudget, and we want to reuse a part of it, partially retrain the model for a new task, task B, usually on a very much smaller data set with much less compute resources, and we get out a model specialized for task B. So how do we go about this technically, and why does it actually work? What is the intuition? The intuition here is that the convolutional part, the deep convolutional layers of the pre-trained network, they contain generalized knowledge about how to process images. For example, detect edges, objects, object composition, and so on. That's our hypothesis here. This knowledge, this capability is not specific to ImageNet. So we can just take this and reuse it. So we take these first convolutional layers, including the weights, we freeze it, we take off the ImageNet specific classification part and attach a new classification part for our flower classification. And we only retrain this specific classification reusing the weights of the convolutional layers. And we're not going to show you a lot of code on the slides. You have that in the notebooks. But these few lines of code show that there's great library support with libraries like Keras for transfer learning. Not only do they let you download the MobileNet V2 with the ImageNet weights, but they also expect you to only download the top. That's the include top equals false argument. Then you plug it together with a custom classification part. And as you can try for yourself, with only a few minutes of training on a laptop like this, we get a decent flower classifier with minimal engineering. So transfer learning at a glance. We're adapting a model to a different task. The way we do it means that the model size stays roughly the same, also the inference cost stays roughly the same, but we can get away with much, much less training data and training cost usually. And as you will see when you look at the notebook and run it by yourself, the development effort is really small due to good library support, so it's a pretty simple technique to try.
The second method we want to introduce you to is distillation. Let's assume we have some large model that somebody else has trained, and it's doing its job really well. But being such a large model, it's a bit of a pain to deal with. Like for inference, in deployment, we need quite a bunch of resources. And honestly, we'd kind of prefer something smaller, a bit more flexible, but that still needs to get the job done. And this is where the fusion comes in. So we're taking a large model trained by somebody else, and we're using that model to teach a smaller model. And easiest to see how that works is by looking at an example. Perhaps many of you have heard of the OpenAI Whisper model. It's an audio transcription model. So basically, you put in an audio file and it returns to you the transcript of the words being spoken in that audio. It's a fairly large model at 1.55 billion parameters. and it was trained on nearly 700,000 hours of audio and transcript. Not too long ago, Hugging Face came out with a model called Distill Whisper, which is, well, a distillation of Whisper. So let's look at how they trained their Distill Whisper. They started, of course, with the original Whisper model from OpenAI and put through it some audio file and got returned, as we've seen earlier, the transcription. They then feed that exact same audio file also into the small model, together with that transcription, and use that to train the small model. Which basically, if you think about it, means we don't need annotated training data. We don't need to have the original transcript of the audio. We can make use of the large Whisper model to generate those transcripts for us. This is huge. It's much easier to find a bunch of audio clips than find a bunch of audio clips that also have been transcribed. It turns out that actually Hugging Face is tying these models even further together. So in addition to feeding the transcribed audio, they also feed in for every time step of the audio file the prediction for the next word that is probably going to come up. And we'll see in a second why they're doing that. We've already seen one of the big benefits of distillation. That is, we need much less, perhaps even no, annotated training data. But there is a second aspect that I would like to talk to you about. There's a good chance that if we had the original 700,000 hours of audio and transcripts and used those to train our small model, we still wouldn't have achieved as good a model as we can through distillation. And that seems really, really unintuitive, doesn't it? So let's look into it. Why could that be happening? If we take a step back, we kind of have to admit that the way we're training our models is quite harsh. Let's assume we have some image classifier and we feed it an image of a large ship. We want the answer to be ship, which certainly shouldn't be football, but it also shouldn't be boat. We punish every mistake. But if we look at the right-hand side on those predictions, they don't actually look that bad. In fact, they might even be a sign that the model is starting to generalize a little bit. It does make sense to mismatch a little bit between a ship and a boat. It seems maybe the model has started to get a general idea of things that float on water. And it seems really, really counterproductive to punish this. So it turns out that large language models can learn despite this harshness that we are putting them through. But small models, they sometimes struggle. Why that is the case, we don't really know yet. This is an area of active research, and I just hope that I can convey to you some intuition of what is going on here. So, what distillation then does, it does create a much more friendly learning environment in which even small models can thrive. Instead of feeding those hard labels, we feed in the soft predictions in a way already interpreted for us by the large model. And this way, we can train the small model much better than if we trained it from scratch with the original hard labels. In this way, the Still Whisper ends up being 6 times faster, 50 times smaller, and with nearly exactly the same performance as the original model, at least for English, at a cost of only 2% of the original training data. And I think this is completely amazing. In our companion repo, you will find a notebook about Whisper and Distill Whisper. and you have a chance to transcribe, to use Whisper and Distill Whisper to transcribe, hear and see for yourself how well they are working. To summarize, we can distill a large model into a much smaller model with nearly the same performance and only a fraction of the original training data. But I must warn you, distillation is newer. Library support is not as good as transfer learning, so getting up and running with it will be more complex compared to transfer learning.
Microbudget method number 3, quantization. That's a hot topic right now because it's one of the factors driving the, I should say, explosion of open LLMs that you can run on your local machine with modest hardware, but a bit more on this later. What's the basic question we're asking here? The question is, do we really need the full precision of floating point numbers to represent the knowledge that's in the model, to represent the model's weight? If we could manage to represent the same knowledge with, for example, 8-bit integers, we would have a 4 times smaller model file, 4 times smaller model footprint in the memory. And also, if we can do the compute, the inference in integer, 8-bit integer, then we can have a 2 to 4 times faster inference. So it would be great if we could manage that. How can we attack this problem? We have the original distribution of weights, unquantized, in float 32, and we want to map them to 8-bit integers. So 256 values from minus 127 to 127. And this can be done by fitting 2 parameters, a scale factor, and a zero shift scalar, basically determining the 0 point of the new distribution. And then the quantized weights result by a simple formula in the top right from the original weights. So in practice, what would we do? We would go through each component, each layer, channel, and so on, and analyze the weight distribution to calculate the parameters S and Z. Then we apply the quantization formula, and we store only the quantized weights. So float 32, int 8, 4 times smaller weights. Great, we have a smaller model file and a smaller footprint in memory. But we haven't taken care yet of computation. What happens during computation? We also want to perform the inference in the lower precision data type. We can apply basically the same strategy to the activations of the network. However, for that, we need to determine the distribution of activations, and we do that by running the forward pass of the network with a few samples. Then the principle is basically the same. We calculate the 2 parameters and we map the activations also to the reduced precision space. And that gives us, if we can do only integer multiplication instead of floating point multiplication, 2 to 4 times faster inference. Can we drive this even further? So 8 bits is not small enough. Can we go for 6-bit, 4-bit, or even 2-bit quantization? Yes, those are all common. Those are being done. And you might ask, what are the capabilities that we are sacrificing? If we are so strongly compressing a model, we must lose something. And that's true, we have to expect some capability loss. It's hard to predict upfront. The models vary in their sensitivity to quantization, so you need to evaluate the capability loss experimentally. Question for the microbudget, do we have to do all the evaluation by ourselves? Well, luckily, quantized models are being provided to us in many cases, and the model card also recommends a particular quantized version that works well and maybe warns you if the capability loss is so large. So by radically quantizing, we can make the model file here up to 16 times smaller for 2-bit quantization. But we are going to pay for that probably with some capability loss. In our companion repo, you are going to find a notebook that shows you, first of all, how to run a quote-unquote large language model on your local machine. A laptop like this one should be enough, with a great tool called Olama. And we also show you how to get different levels of quantization for a particular model, host all of them with Olama. It's an easy workflow how to integrate it into Olama. And then you can test and observe the capability loss, the development of the capabilities. And since we're in the impressive city of Florence, we're asking the model to recommend us an itinerary for sightseeing. I invite you to try it out, but maybe fact check the 2-bit model before you go out and look for the Leaning Dome of Florence. So as I said, the OpenLLM ecosystem thrives on quantization. It enables us in the first place to run even medium-sized models on modern hardware. Takes 15 billion parameters in 9 gigabytes of RAM. And it also makes the distribution of these large files much easier. So as a consequence, many of the models that the Olama catalog is hosting, they're quantized by default. I've often seen 4-bit quantization as the default. So at a glance, we are getting a model from quantization that's potentially as capable as the original, depending on how much we quantize. We can make it much smaller while sacrificing very little of the capability. So we also speed up the inference. And the process of quantization, for that you need a lot less training data and training resources to perform that if you want to perform it yourself. Applying these models, as you will see from our notebook, is quite easy. Olama helps us here. I'm joining the crowd of people praising Olama. It's a great tool for getting started with your local open LLMs. So that's the end of our presentation. We'll leave you with this overview slide and would love to start discussion and taking questions here. Thank you.
Thank you very much for the very insightful presentation. Are there any questions in the room?
When you use smaller quantization, you are using data types which are not really able to be handled by the CPUs or GPUs normally. So you need packing, unpacking, data shifting, something like that. So you are wasting a lot of resources and computational power for that. How these is going to be useful for people which are using those local models, because you want to execute those models on your laptop, your PC. And this requires much larger computational power for handling this data format which are not native.
Okay, yes, you're right. If you don't have specialized hardware, you will, well, at the very least, benefit from the model size being smaller. But it might be that whatever framework you're using actually unpacks this back into the original data type, and then you haven't really won anything in terms of computation. What we are seeing is actually people developing quantization schemes as well as hardware in combination. And if it's not already the case, I expect these kind of things to also be in mobile phones and computers at some point, so that you can directly benefit from the quantization also on a hardware level.
I saw another question.
When you were talking about the quantization, especially the 2-bit quantization, I was thinking about, well, it is real faster, but probably the output is not the same as the original. So are there any studies about like an ensemble method of quantization with 2-bit? I mean, it's real faster. Is it possible to mix some of these 2-bit quantization together to have a real good output and like stay always faster than the original model?
That's an interesting thought. I don't think I've seen any research towards that. I don't know if you've seen anything, but I mean, assembling multiple smaller models to, in combination, perform better than each of them individually. I mean, that's a pretty standard strategy. So I'd expect that this actually gives you some benefit. Yes.
Hi. Again, about quantization, I imagine there are a lot of weights in the model which are statistically not very significant. So I was wondering if it is possible to perform like a statistical analysis of activation to decide not to quantize all the weights, but just the least significant ones.
Yes, completely correct thought. There's a field of activation-aware quantization. We just kept it simple for this talk and for the examples and didn't dive into that. But definitely there's active research and also practice in that direction.
I have a question online. Is it feasible to train in integer domain?
So we've introduced post-activation, post-training quantization. There is also quantization-aware training, but then you don't actually train in the integer domain. Rather, you keep an integer as well as an original precision copy of the weights. The reason for that is the gradients that we are applying, they are quite small. They're too small and too fine-grained to be captured by the integer. So basically, we run the forward pass both with the integer and with the full precision weights. We calculate the gradients and then apply these gradients to the full precision weights, and then do the quantization again to get to integer weights. It's probably going to be better than post-training quantization because you're already kind of pushing the model into expressing itself, if I may, with these 255 or even less values, but directly training in integer, no.
Thank you. Any other question?
About distillation, I saw that example that you showed about the model that has been trained upon data upon a bigger model. Wouldn't that be risky? I think it just inherits the weakness of the first model and its mistakes. It doesn't learn from mistakes, but it learns mistakes to reproduce that.
I mean, you're not going to be ending up with a model that is more performant than the original model. That's not possible. So whatever the original model is doing wrong, the new model is likely also going to be doing wrong. So yes, take a good starting point before you do distillation. Make sure that the model that you're distilling is actually doing what you need it to do.
So to clarify, in the best case, you preserve the capabilities of the original model, but you can make it much smaller. That's the micro-budget approach here.
Thank you. We have time for a very quick last question, if you have one.
Can you combine distillation and quantization?
I kind of was waiting for that question. I'm sure people are looking at that, yes. So for me, I think Chris disagrees a little bit. Both of these methods, they feel of kind of, we have these large models and we perhaps needed to have them that large to get them to train. But whatever they have, what kind of knowledge they have can be condensed. Now, if we do two types of condensations, maybe we're going too far. So probably you need to find some good equilibrium there.
I think we have also time for yours.
Can you do multiple distillations? I mean, I take a larger model, I distill into a still large model, and I do subsequently distillations until I reach a much smaller model. Does it make sense, or one distillation is enough?
I've seen some work on iterative distillation, indeed, yes. I don't have the stats right now, how much that adds.
Okay, thanks.
So thank you very much for your talk. That was very, very good.
Thank you all.